Hi, thank you for listening to this presentation. My name is Mathieu Dorier. I'm a software development specialist at Argonne National Lab, and I will be presenting a work led by Nathanael Cheriere, a former PhD student of ENS Rennes, who graduated in late 2019. This presentation will be about Pufferscale, a microservice component for enabling elasticity in high-performance data services and its application to a specific storage service for high-energy physics. So in many, if not most distributed applications, we often observe variations in the requirements for computation resources. In the cloud, we have day-night cycles that are common, for example, for applications that interact with users. But this variability can be generalized to applications running on supercomputers as well, in particular if they are organized in workflows or treat unexpected workloads, for instance, coming from scientific instruments. Resource management is more complex when applications have to deal with varying and sometimes unpredictable workloads. In these cases, elastic resource management helps. An elastic resource management system is able to increase and decrease the number of resources as needed based on the application's dynamic requirements. Such elasticity has multiple advantages. The application will always run nominally, even in the presence of unexpected workloads. It minimizes the cost for the user, whether the user is renting computation resources or burning core hours out of a project allocation on a supercomputer. It also enables better resource utilization for the platform overall, and in that sense, it's also beneficial for platform administrators as well. In practice, this elasticity is available mostly in clouds and when talking about computing resources such as cores, nodes, or VMs. However, while applications can often easily be made elastic, it's not the case of storage systems they use. Usually, the storage systems remain static. This poses two problems, at least. First, a static storage system may be too small to absorb the I/O activity of the application, or it may be too large and wasting resources. The second problem is that the static storage system paired with an elastic application must necessarily be deployed on a separate set of resources. It cannot be co-located with computation, which means that the application cannot benefit from access locality or simply from storage resources located on the same compute nodes. So why don't we see more elastic storage systems? Well, the answer to that question is often that rescaling a storage system requires migrating data, and this takes time. Yet with faster networking technologies and faster storage devices, migrating data should become less of a problem nowadays. Assuming that data migration is fast enough, and an elastic storage system brings multiple advantages, including being able to rescale at will to provide more bandwidth to the application, or to add more storage space. The implementation of an elastic storage system brings two sets of challenges. The first set concerns decision making. When do we rescale? Why? How many nodes to add or remove, and which nodes? The second set of challenges concerns the malleability, that is, how do we implement this elasticity in practice? This malleability will be the focus of this work. Narrowing the focus down further, we will be interested in user space storage services in high-performance computing. These services have emerged in recent years to avoid using parallel file systems. They are generally tailored to the application or to the set of applications that they aim to support. They store temporary data while the application is running, and they generally provide lower latency and better throughput than the traditional storage system like parallel file systems. These systems run on compute nodes allocated by the users, so there is a need to optimize their resource utilization to achieve the best application throughput while minimizing the extra node allocations for that. Examples of HPC data services include the collection of services built in the context of the Mochi project, and this is the framework that we are going to use in this work. Mochi is at the core of a collaboration between Argonne National Lab, Carnegie Mellon University, Los Alamos, and the HDF Group. It focuses on providing a set of building blocks that can be composed together to build HPC data services that are tailored to specific applications. For instance, Mochi provides key-value storage components, bulk storage components, database components, and so on. It relies on Argo bots for threading and on Mercury for RPC and RDMA. Most importantly, Mochi emphasizes composability of its building blocks, namely to build a new data service, you take the building blocks that you need, you compose them together, and you put the right interface on top. This composability aspect will pay off later in this work as we will be able to provide elasticity features via two new building blocks, one that handles data migration across nodes and one that monitors data placement and load on compute migration plans. Mochi was used in particular to build Hypnos in the context of a collaboration between Argonne National Lab and Fermilab. Hypnos is a distributed storage system meant to store events. Events are small objects packing some metadata and some data coming from runs of a particular accelerator or produced by subsequent analysis workflows on a supercomputer. They are stored by Hypnos in a number of in-memory key-value stores called buckets. Each process of the storage system manages multiple buckets, a bit like each storage server in a parallel file system manages multiple storage targets. Hypnos will typically be deployed for the duration of an experimental campaign and remain deployed on some compute nodes to serve possibly multiple applications. These applications have different needs, which brings us to the need for Hypnos to become elastic. We want to be able to downscale and upscale it as needed. However, not all the events stored in Hypnos are equally important. Some events will be accessed more frequently than others, and in consequence, some buckets will be accessed more frequently than others. This brings a challenge in our quest for elasticity. We need to be able to rescale fast under constraints of some load balancing. Load balance represents some user-defined metrics of how important some pieces of data are, correlating with how frequently they will be accessed in the future. Ensuring load balance avoids hotspots by making it more likely that the application's request will spread evenly across servers. Load balancing here should be distinguished from data balancing, which represents how balanced the amount of data is across nodes. However, data balancing is important too, and it becomes especially important when we start talking about elasticity. If our storage system is unbalanced with respect to the amount of data per node, as shown on the left, then, for instance, removing node E will take time because 1, more data needs to be migrated out of E, and 2, we will also migrate more data from node E to node D or B. On the other hand, if the system has balanced data, then decommissioning any node will involve a minimum amount of data migration, and this data can be migrated equally to all the remaining nodes. So in the end, we have an optimization problem with 3 objectives: speed, data balancing, and load balancing. To formalize this problem a little more, we can define the load balancing as the maximum load found on a node. The data balancing is defined as the maximum amount of data found on a node, and the transfer duration is defined by looking at the maximum time any node needs to send its entire set of data to other nodes, and the maximum time any node needs to receive data from other nodes, as a function of the old and new data placement. These target metrics should be minimized under constraints related to the capacity of the node, the fact that, of course, we cannot lose data in the process, and the fact that there shouldn't be any data remaining on nodes that are being decommissioned, so that are being removed. The problem with this optimization is that finding an exact solution is simply impractical. Since we have 3 objectives to minimize, there is no single solution. There is a set of solutions forming a shape in a multidimensional space, such that from any solution, any attempt to improve one objective will necessarily be detrimental to at least one other objective. So instead of computing this set of solutions exactly, which can take a very long time, we need a heuristic. First, instead of moving single events, since events are already gathered in buckets, we will migrate buckets. This drastically reduces the number of objects for which we have to make a placement decision. Second, we use a greedy algorithm that mainly works as follows. We compute the target value for each objective. We then leave the biggest buckets where they are as much as possible, and we find placements for other buckets to minimize the least minimized objective. Of course, we can also use weights for each objectives to put more importance on one or on the other. For instance, more importance on data balancing, on load balancing, or on speed. To enable this elasticity in Hypnos, we implemented Pufferscale, a rescaling manager whose task is to execute the algorithm I just presented. Pufferscale is a Mochi component, so it can actually be used in other data services based on the Mochi technology. It is independent of the storage system. In Hypnos, storage is done using key-value databases, but Pufferscale would work just as well with other types of storage components as long as you can provide a function to migrate a component from a node to another. Pufferscale will track buckets, their size, their load, and it will organize rescaling operations and issue migration instructions. Pufferscale is composed of a controller, which will send rescaling orders to a master component. The master component does the migration planning, then issues transfer instructions to worker components on each node of the storage system. Each worker component interfaces with the underlying storage microservice via callbacks and asks the microservice component to migrate its data to another node. Pufferscale does not do the transfers itself. Transfers are handled by another microservice called REMI, a component capable of sending files from a node's local storage to another. We evaluated Pufferscale on the Grid 5000 platform on a cluster with 65 nodes. We did two types of experiments. We evaluated a very large storage cluster to test the heuristic, but without actually performing any data transfers. This lets us evaluate Pufferscale's heuristic at large scale in a short amount of time. Then we did smaller scale experiments with actual data transfers. In this first experiment, we aim to evaluate the heuristic itself, so no data transfers are actually done. We simply estimate the time it would take to do them. We are looking at two operations, the commission of 64 nodes to a cluster that has originally 320, and the associated decommission. In between two such operations, we do 9 random rescaling that reshuffle the buckets between the nodes. We compare two strategies, LT in red, that only optimizes for speed and load, and LDT in blue, which optimizes for the three objectives. When comparing the two strategies, we can see they differ most on two aspects. LDT has a better data balancing than LT, which is expected since LT does not balance data. Concerning the duration of the rescaling, there is less variability with the LDT strategy, and it is faster in the case of a decommission compared to the LT strategy. The load balancing is very similar between the strategies. Another important thing to notice is that the heuristic only took 600 milliseconds to compute the data transfers, which is just a fraction of the 10 seconds that are actually required for the transfers themselves. We claimed earlier that data balance is important for the speed of rescaling operations, and we show that with this experiment. Here we compare the same two strategies as before, but starting from different situations. To obtain this graph, 9 random rescaling operations are done with LDT. Then we studied rescaling operations done with either LT or LDT. In other words, LT and LDT start from the same configuration, which is data balanced, and we observe in this case that both strategies are very similar. When we compare this result to one from the previous experiment, we can highlight that data balancing is important to ensure faster subsequent rescaling operations, but does not speed up the rescaling operation that enforces data balancing. For the second set of experiments, we use the storage microservice described before and studied its performance. We configured the storage microservice to manage 256 buckets that are stored in memory for a total of 128 gigabytes of data. With this, we studied two rescaling operations, scaling up from 48 nodes to 64 nodes, and scaling down from 64 nodes to 48. With the actual implementation of Pufferscale in a microservice, we obtain the same results as the emulated storage system. Adding data balancing does not change the commission and speeds up the decommission. In our case, the decommission was sped up by 13%. Before concluding this presentation, there is one important aspect to highlight. Data balancing is important in Pufferscale because our use case, Hypnos, does not rely on data replication. If we had data replication, the load balancing would be less reliant on data placement, since each request can be executed on any of the nodes hosting a replica of the required data. And based on the same principle, the choice of the node sending the data during a rescaling operations is facilitated by the presence of replicas. These two facts greatly relax the problem and make Pufferscale unsuited for storage systems with data replication. So in this presentation, we studied the problem of rescaling storage systems such as Hypnos. We identified that data balancing is important. We formalized the problem with 3 objectives and proposed a fast heuristic to decide how data should be transferred during rescaling operations. We implemented the heuristic in Pufferscale and showed the decommission can be indeed sped up by ensuring data balancing. Thank you for your attention.